Hello? Oh, okay. Good afternoon, everyone. My name is Kai Ning Zhang, and I'm from the University of South Australia and the Pacific Computing Lab. Today, I'm very excited to present our work titled Head Zoom, the hand-free zooming and panning navigation for the 2D image using the hand motion on behalf of all my courses. And this is a collaboration work between the University of South Australia, University of Technology Sydney, and University of Lisbon, and led by the Professor Joachim George. And in this study, we explored how the natural head movement can be served as a natural head movement and used as an input method for the navigation in immersive environment. So let's start from some background. The 2D image navigation is a common task in mixed reality. It usually involves zooming and panning to explore the visual content. And traditionally, this requires a careful visual attention and precise control. Most often use the hand or the handheld controllers. Such techniques are often applied in domains like the navigation spatial maps, medical image, and also the digital photographing. However, in the real-world MR scenarios, users' hands are often occupied, so the hand or controllers are not always practical. And also, the existing hands-free method also have some limitations, such as the speech-based method. They suffered from the latency and the noise. And the eye gaze-based method, they lead to some unintended activities and also fatigue. And existing the head gesture-based method, they only allow the discrete zoom steps without the continually panning. So this highlights a research gap, how we can create a natural and precise way to zoom and pan in a real time with the head movement. Given those limitations and the research gap, we designed Head Zoom. We built Head Zoom in MetaQuest 3 and developed with Unity. And the diagram on the right shows the overall precise pipelines. We use the head motion as input, and head translation control the zooming and out, just like a dialing effect. And we use the head rotation, yaw, and pitch to control the panning through the recasting. We choose the Kalman features to ensure the smoothness because the raw head tracking data can be very jittery, especially when you have a very fast head movement. We also designed our collaboration steps before the task. This is very important because to avoid, we can use this method to avoid the unnatural head pose, and also the task can serve several minutes, so it's very crucial. And user can lean forward and backward to define their personal comfortable maximum and minimum zooming and zoom out range. And then we design 3 interaction mode. First, static, which serve as our baseline. In this mode, zooming works in the just like the real world. So user can physically move close to the image, but the image still fixed, cannot move. And there's no head-based zooming was applied. Then the parallel mode. In this mode, the zooming is controlled by leaning the hand forward and backward, so the image can move with the head. And where the panning is done by moving the image down a fixed plane. And finally, tilt. For the tilt mode, the zooming is similar to parallel, where the user can zoom in and out by the leaning forward and backward. But the panning is a little bit different. So the image itself can tilt, which can allow the user to bring more specific part of the image more closer. So across those modes, we can see the static mode can stimulate the real-world viewing, and the parallel can provide the head-based zoom with the fixed plane panning. And the tilt can combine the head-based zoom with the magnetic ray orientations. And each mode, they offer a different balance between the ease of use and the control effort. So here are some demos of our zooming and panning in each mode. And this is the panning. Okay, and for our user study, we use the find valley task. We select this task is because it's naturally required both zooming and also zooming for details and panning across the scenes. And it also widely used in visual search task. In this task, participant had to locate valley in a very complex image. And in each trial, participants use a signed interaction mode to move a red selection circle over valley, and they need to use a controller trigger button to confirm their choice. And each image we allow they have 2 minutes and up to 3 times guess. The trial is ended as soon as the volley was correctly founded by the by the trigger button within 2 minutes, or the time limit reached, or the 3 times guess reached. So for this study, we recruited 31 participants, 16 females and 15 males. We applied within subjective design. Each participant, they complete search task under 3 interaction modes in a randomized order. And in each mode, they complete the search task at 2 difficulty levels, the easy and hard, with image randomly assigned. Having both easy and hard image can help us to test whether the technique works consistently across 2 different cognitive loads. And after each interaction tasks, and participants, they read how easy or hard it was to find volley with that mode. And at the end of each mode, they fill a post-scenario questionnaires. And finally, after all 3 modes, they fill a post-experience questionnaire to compare those 3 interaction modes. So to evaluate those 3 interaction modes, we look at 3 categories. First, the physical domain, how much head movement or rotation were required, plus the zoom usage and the lean distance. And second, the task performance, including the completion time, success rate, and the false positive. And finally, the subjective measures, including participants' difficulty ratings and usability score and overall preference. So here are the results on the physical domain. We find that in the static mode, the participant, they need the largest amount of the head movement or rotation to complete the zooming and panning-based task. And for the parallel mode, that was the most effective method, which showing the least head movement and rotations for all those tasks. And tilt mode fell in between. And this radar chart on the right make it more clear. We can see the yellow circle is from the parallel mode, and this shows it requires the least physical effort overall. So where the physical effort are clearly different, but we can see the task outcome are largely similar. We find actually there is no significant difference in the task success rate, completion time, or the difficulty rating across all those 3 modes. However, we can find there's something interesting in the preference result. We can see the most participants, they preferred parallel as their top choice, while the tilt was most often rated as the least preferred. And the static, they sit somewhere in the between. So here are some summary of our key findings. First, in terms of the physical demand, the parallel mode requires the least head movement and rotation, and static requires the most, while the tilt was somewhere in between. This suggests that parallel mode can have the less fatigue for the long-term use. And second, when we look at the user preference, participants clearly prefer the parallel mode, and tilt was the most often rated as the least preferred, while the static received a mix of options. And third, performance. All those 3 modes show similar completion times and the success rate, which means they are equally effective for the visual search task. And finally, in terms of the usability, all those 3 modes scored very high on the SUS score, around 80 points, with no significant difference. So overall, where the performance and the usability were largely similar, but the parallel modes still stand out as the most effective and most preferred options. And based on our findings, we proposed the 5 design guidelines for the hands-free interaction in mixed reality. First, we should consider the minimized effort. So we can see from the parallel mode, because it reduces the head movement, and it's showing that design should avoid the unnecessary physical domain. And second, we also should consider the stable input. So we can use some smoothing like the Kelman features to help reduce the jittery and improve the control. And third, ensure the spatial consistency. We find that the tilt mode can cause some spatial confusion, so the image behavior we should consider stay more predictable for participants. And fourth, we should maintain a stable view, because the static task can slightly faster the completion time, which suggests that keep the view stable can help users to search more effectively. And finally, we should also consider balance of the control and the simple, because we find that actually all three modes score very high on usability, which remind us that even the very simple but consistent method also can be very effective. So you may ask where it can be useful. So here we provide two examples. One example is a geographic information system like the navigating Google Maps. Another one is in the medical image, where the radiologist can zoom in and zoom out to the X-ray. In both scenarios, the head-based zooming can provide hands-free and smooth interaction. And our study also has some limitations. First, we only test the 3 interaction mode, and our study was conducted in a controlled lab setting, and we only focused on a single task, and also our evaluate in a very short term, so which may not able to capture the long-term effect. Looking forward, we are planning to explore the multimodal combination like the head plus gaze, and extend the head zoom to different tasks and application domains, and also invite the long-term use in the real world. So to conclude, our work makes 3 contributions. First, we introduce a head-based framework for zooming and panning in MR. And second, the user-centered design. We designed and tested 2 normal techniques, parallel and tilt, against a static baseline. And last but not least, we provide findings from our user studies that highlight the strength of the parallel zoom. So overall, our results show that head motion can be served as an effective and economic hands-free input method. So thank you for your watching, and for more details, you can scan the QR code for our paper preprint. And finally, because I'm nearly finished my PhD, so I want to say I'm currently seeking a postdoc or lecture jobs in the HCI field. So if you know any suitable positions, I would be very grateful if you can let me know. Thank you very much, and I'm very happy to take any question now.
Thank you. Right, so we have 3 minutes of questioning. We have 2 microphones, one over here and another over there. Are there any questions? In the meantime, okay, we have one.
So is this framework available for download for us to play with, or is it in a GitHub repo that we could download?
Sorry, can you speak a little bit loudly? I can't.
Yeah, is this framework available for download on GitHub?
Could you repeat the question?
Yeah.
Sorry,
So,
put the microphone close to you.
So could we download this framework and play with it, or is it in the GitHub open source code base, or is that your own framework?
I think in the future will be the open source, but now is because the paper haven't really published yet, but after our publish, we think we may consider to make it open source.
Oh, thank you.
Yeah, no worries.
Any other questions? I have one. I have tried similar system in the past, and I got very sick. Did you try to measure simulated sickness or anything like that, or do you get any feedback on how sickening each condition were?
Yeah, actually, thank you for the question. We actually have this question in the post-condition questionnaires. So actually, we also report this result in the paper because all those 3 modes shows very low motion sickness. So we didn't report as the main result, but we did this question. And also the reason is also because maybe our test is quite short. So in the future, I also mentioned in the future we will try the long-term use, and maybe we also need to consider the sickness at that moment.
Thank you.
Yeah.
If there's no more, oh, there's one. Yep.
Thank you for the interesting talk. I think I have the question is about the concept of zoom itself. Zoom on a flat screen is very straightforward, but zoom in a VR environment can be interpreted in different ways. Like in your research, it's about actually not strictly speaking zoom, but move the image plane closer to the viewer instead of enlarging the scale. And I think another way that we can interpret the zoom in a VR world is like looking through a telescope, like that change the internal FOV, so that you are looking at a very small area but very distant. So have you thought about trying other forms of zoom in a VR environment?
I think that's a good question, and also very good point. For current stage, we only tried those three, but like what I mentioned, later on we might explore more and more interaction method, because now it's kind of like the feasibility test for the head zooming, and I think we still have a lot of space to improve it, and thank you for your suggestion.
Okay. Hello, everyone. I'm Sung-Ho Jae, from the School of Design at SUSTEC. I'm leading immersive design group, and I will introduce our fantastic research. So, designing hand and forearm gesture to control virtual forearm for user-initiated forearm deformation. This paper collaborates with great researchers, led by Irong Lin, Han Shi, Wei Tao Zhang, Sui-Shun Zhang, Hye-Young Jo, Yoon-Ji Kim, and me. Actually, originally this paper was planned to be presented by my handsome, lovely, smart, awesome master student, Ilong. But unfortunately, he just started his PhD in UK, so handsome and generous master supervisor, me, I will present instead of him. Okay, so why are we interested in forearm deformation? Think about when you watch rubber heroes like Luffy or One Piece or Mr. Fantastic from Fantastic Four. They can stretch and twist their arm in a crazy ways. And I think maybe many of us have had the same thought. What if I could do that myself? So this is the motivation. So this is where virtual reality comes in. VR gives us unique chance to go beyond the physical limit of our bodies. Instead of actually changing our rear arm, we can experience and even control different deformations through our avatars in VR. So one example of the beyond rear interaction is I'm a Giant, where researchers scaled the avatar's body to let users work faster in large environments. By making the avatar bigger, user could cover more distance with each step, effectively extending locomotion beyond normal human's limit. Another example is ninja hands. Here, a single rear hand was mapped to multiple virtual hands, allowing users to reach and select distance objects more quickly. Within this broader category of beyond rear interaction, many works has focused more specifically on arm deformation. Previous research have tried some creative approaches. VibroArm, our previous paper, used vibrotactile funneling illusion to enhance the sensation of forearm deformation. Gum shifting combined the weight shifting and skin stretching to make the arm feel elongating. And the very long arm illusion studied how different amount of elongation affect people's sensation of ownership. More recently, some research has begun to explore user-controlled body deformations. For example, this paper investigated seamless visual transition that allow avatars to change between body types. However, they focus was on full body adaptation, not specific limbs. And Wangs and others demonstrated in their miniature haptic system how user can control full body avatar movement using hand gestures, showing the potential of gesture-based body control. So we already know the illusion can create the feeling of deformation, and that user can even actively control avatar deformation in VR. But what's still missing is forearm-specific control. Most of previous work has focused on system-driven passive illusion, where the forearm deformation is triggered for user rather than by the user. What's still unexplored is whether users can actively initiate and continuously control forearm deformation themselves. In other words, we don't yet know how gesture-based input can provide precise, embodied, and intuitive control of beyond rear forearm deformation in VR. To address this gap, our research follows three main steps. First, we conducted a gesture design workshop with 6 designers who created and refined gesture sets for forearm deformation. From their work, we selected the top 3 sets and implemented that. Finally, we carried out a user study where we systemically compared these 3 sets in terms of embodiment, workload, and task performance. In our gesture design workshop, we recruited 6 designers, as I mentioned, to create gesture sets for forearm deformation. We gave them a few design requirements. First, gestures should be natural, physically simple, and easy for device to recognize, learn, and remember. Second, we emphasize the Midas touch problem, where unintentional movement might be misread as gesture. To avoid this, designers were asked not to use common everyday gestures. Finally, guided by previous research, we restrict the design space to gestures of the hand and forearm. Our workshop lasted about 3 hours, and it had 4 main parts. First, we gave the designers a short background talk about forearm deformation illusions. Second, they got hands-on with the Vive headset and limb motion just to get familiar with how gesture capture works. Third, we moved to the main design stage. Designers brainstorm gesture in pairs, tried them out in VR using Wizard of Oz setup, and refined their ideas. And finally, we collected all the gestures, 12 sets, and had the designers rate them. From there, we selected and implemented the top 3 gesture sets for our study. Set A is the build around the thumbs and wrist. To activate the deformation mode, the user does a quick thumb double wiggle. Once active elongation is controlled by opening the thumb angle, while shortening is done by sliding the thumb across the other fingers. And finally, the bending direction and extent are controlled through the wrist rotation. Overall, this set is compact and places less physical demand on the user. Set B uses a body-related mapping. To activate, the user opens the hand and at the same time simply move the hand toward or away from the body. Moving it away elongate the forearms, while moving it closer, shorten it. For bending, the user performs a finger spread combined with wrist rotation. The rotation direction determines where the arm bends, and the amount of finger spread controls how much it bends. This design emphasizes spatial intuitiveness because the gestures are directly tied to the body's reference frame. Set C take a different approach. It has no explicit activation mode. It uses a posture to activate. For elongation, the angle between the thumb and index finger is used. Bring the thumb closer to the index finger elongates the forearm. To shorten, the user simply curl the index finger inward. For bending, the direction of the index finger defines where the arm bends, while the thumb's index angle controls how much it bends. This design was inspired by pinch-like interaction, aiming for directness and the continuous control. Difficult to understand through the voice, right? Let's see the video. It's much more easy to understand. So the top one is set A, and the left is set B, the right is set C. So as you can see, we attach the optic tracker, and then you can see clearly like how we can control using these 3 different sets. So after implementing these 3 gesture sets, the next step was to ask, how do they actually perform with users? We want to know 3 things. First, do these gestures still allow users to maintain the strong sense of embodiment? Second, do they add extra workload, or are they easy and comfortable to use? And third, which step provide the most efficient interaction in practice? For the study, participants were the Vive headset and the optic track tracking the captures. During the test, they had elongating, shortening, or bending their virtual forearm in order to reach the target ball that appeared at random position. Here's the short video. So this is how participants activating a gesture set, deforming the virtual forearm, and interacting with the target. Our research shows that these three main things. The first, workload. Set A was rated lower than set C, meaning it felt easier to use. Second, embodiment. Set A and set B generally outperformed than set C. And the third, task performance. Set C was the faster for elongating, but set A was fastest for bending, and overall, it gave the best performance. From the result, we can clearly trade off across the three gesture sets. Set A, best for bending. Its design relied on fewer hand joints, mainly the thumb and wrist, which made control more precise while still maintaining a strong sense of embodiment. Set B was particularly effective for shortening. Set C drew on familiar gesture vocabulary, but its mapping was less direct. As a result, embodiment score was weaker, even though the gesture felt familiar. From this finding, we can draw several design guidelines. First, we should match gesture complexity to task requirement. Second, we should align gesture with the biomedical expectations. Third, we should prioritize intuitive mapping over familiarized gestures. Together, these guidelines highlight that gesture design must balance intuitive mapping, biomedical efficiency, and task-specific demand, rather than applying a one-size-fits-all approach. Of course, we have limitations. First, we used the Wizard of Oz in the design workshop. Maybe it limited the imagination of the designers. Second, our implementation depends on physical markers. So we have to invest more time to use the other tracking systems. And also, finally, our study focused only on forearm gesture. We have to invest in other body part. In the future, we have to explore consumer-grade solutions such as kinetic, quest hand tracking, and etc. We also will think about multiple forearm and multiple joint deformation and etc. Yeah, this is the contribution, and you can find more detail in our papers. Thank you so much.
We have time for one question. Anyone has a question?
Feel free to ask questions, and even like suggestions also welcome. Let's work together.
So I have a question. Which set was your favorite?
For me, like set C is my favorite personally. Why? Because it's easy to remember, very familiar setup. But as I mentioned, that doesn't mean it's most efficient or most fast. So depending on the task and the goal, but personally, maybe I became like losing my memory capability. I prefer familiarized one.
Thank you. So please give another round of applause for Sung.
Hey everyone, I'm Natalia. So, when it comes to VR input, there are two common options, controllers and hand tracking. But let's be honest, controllers are the preferred approach. In fact, some even call it the default approach, especially when paired with hand avatars. I mean, we see it almost everywhere. Research that we've been seeing today, yesterday, tomorrow, and more further. Also in training and education platforms, exposure therapy, and of course, video games. In fact, before this study, I actually played a VR escape room game with my friends, and it was absolute chaos. We spent 1/3 of the time trying to figure out the controls on how to even escape. And my friends, I would see them standing there, just staring blankly at their virtual hands, perform a million gestures because they didn't know how to grab an object. From that point on, it went downward, as in we did not escape whatsoever. But it left me questioning, why did they struggle so much? And the more I looked into it, I realized it's not just them. It's not just them that has faced this problem when it comes to controllers and hand avatars. There's a well-cited study that actually analyzed over thousands of Steam VR game reviews, and they found that hand avatars that appear static or move unnaturally actually have a very big negative impact on the player's sense of embodiment and immersion. And that's when I realized I had a study in my hand, which brought me here today with our study, comparing hand and controller avatars with hand tracking and controller-based interaction, along with the question we want to address: how do different input devices and avatar representation influence user performance and experience? So for our study, we had 48 participants perform a set of tasks in a 2x2x2x2 within subject design study using the MetaQuest 3 headset. We had 4 main independent variables. The first one being input variable, which was controllers and hand tracking. The 2 avatar variables were hand avatars and controller avatars, both their states either being on or off. Then we had target size variable, which were the targets were either big or small. So by combining all our variables together, we had a total of 16 different conditions within our study that every participant got to experience. And in a single condition, there were 24 trials split between 2 tasks: grasping and pinching. The first 12 trials were actually of the grasp trial. So participants would grab a hammer, hit the center, hit the target, and repeat the process, which was then followed by another 12 trials, which were the pinch trials. So they would pinch a ball in the center, hit the target, and repeat the process again. In every trial, we measured our dependent variables, which were trial duration for speed and the target collision distance for accuracy. Each of our participants performed a total of 384 trials. And after completing a single condition, we had them do an in-game survey that rated their perceived realism and adaptability to the avatar input pairing that they just experienced. And by completing the entire study, they did a post-survey that got their overall experience and preferences. Let's get into the results. I know it's a lot. Bear with me, guys. I swear it gets better. So we found that controllers are consistently faster, more faster than hand tracking as well, but it came at the cost of speed. The speed came at the cost of accuracy, meaning that hand tracking had the overall best accuracy performance. This trade-off that we see between speed and accuracy actually aligns with past research that did compare hand tracking and controllers. But with our study, we could take an even closer look at it. Our data shows that input and visual alignment emphasizes the trade-off between speed and accuracy we found between those 2 input. What do I mean by input and visual alignment? Well, if you're holding controllers physically, inside the VR, you'll be able to see the controller avatars. So a matching avatar, same with hand tracking. If you have hand tracking in VR, you'll see hand avatars. For controllers, a matching avatar reinforced the confidence that participants felt. It drove them to move even faster, but of course that came at a greater cost of accuracy. We believe this happens because they have a solid object in their hand that they're gripping onto. It brought stability, and their physical state matched their virtual state. And also they were able to map out the buttons and feel it, which really helps someone that's not used to controllers. For hand tracking, the matching avatar brought familiarity. It made participants push more towards presenting careful and precise actions within the tasks. Just how we do with our own hands when we encounter a new task. We're more careful. We're not going super fast, but we are accurate. So that's why with this pairing with the matching avatar, it does improve accuracy, but of course it also slows down the participant. This input and visual alignment also enhanced the participants' experience. They said this matching avatar made the experience feel realistic. It felt natural, easy to adapt to. But of course, not every avatar was a perfect match. The avatars that didn't align with the input had a really different effect on the users. So for hand tracking, the no avatar, to no surprise, performed the overall worst. We believe that participants still found use when seeing the controller avatars because it gave them a clear, reliable reference within the virtual space. the no avatar left them with nothing but this tiny little cursor that they have to depend their whole performance on. So, and participants stated that it honestly felt like they were grabbing nothing. They were lost in navigation within the virtual space. So by combining that with the natural instability of hand tracking, it just worsened their overall performance. Controllers were a bit more complex than hand tracking. So for the grasp trials, the hand avatar had the slowest performance, but it did present the greatest accuracy, the same trend we saw with hand tracking. However, with that pairing, participants rated it as less realistic and harder to adapt to, which we found pretty interesting. We believe this happened because though they're seeing the hand avatar, it is a static model. It looks like a hand, but it doesn't really move like a hand, thus violating the participants' expectation of how a hand should behave, lowering their overall realism. For the pinch trials, much to our surprise, the exact opposite happened. The hand avatar actually brought the worst accuracy. It did worse than the no avatar condition. Participants described the pinch gesture as too precise, too demanding, and even some of them stated that it felt more like a video game rather than reality. So pinching, that gesture requires fine motor control between the thumb and the index finger, something participants cannot reproduce when gripping onto controllers. In contrast, it benefits more for the grasp trials. It matches their physical and visual state. Participants even stated that they strongly preferred grasping over pinching. They said it felt more comfortable, more natural to them. So by combining an already difficult pinch gesture with a strong misalignment between what they're doing and seeing, it absolutely just declined their accuracy. Overall, our results show a clear pattern. Hand tracking offers flexibility, especially for gestures that don't map well with controllers, and it encourages keen focus. Controllers offer robust and fast input, but it depends on the avatar design. An avatar representation helps shape how participants approach a task. So we're able to say that input devices and avatar representation are intertwined to one another, and they do influence how users perform and how they experience the overall VR game or application. So it made me start thinking and wondering if in my VR escape room game with my friends, if they saw a matching avatar instead, our data suggests they could have had a better experience. For future work, there's actually two factors we want to target. We want to integrate haptic technology, and we also want to do VR gesture to statistical comparisons. For the second one, in this study, between pinching and grasping, we actually just observed the differences between the two. So moving forward, we would like to actually have more common VR gestures, statistically compare them, and not just say they're different, but actually understand why they're different. In fact, we actually started doing some implementation for the haptic technology, so we're really looking forward to what type of changes we may see from our current study to our future work. Overall, our work challenges the assumption that controllers are superior to hand tracking. It shows that performance isn't just dependent on the device itself. It's also how it's visually represented in VR. Our work encourages researchers and developers to go beyond the default setup of controllers with hand avatars and to actually make deliberate task-specified design choices in their applications. We want to move the conversation away from controllers versus hand tracking or hand tracking is the best avatar, and to actually move it towards understanding how those elements interact with one another, how they complement one another instead. And we believe with that understanding, we can help guide the creation of more immersive, reliable, and user-centered VR applications. Thank you so much for your time, everyone.
Thank you, Natalia. We have 4 minutes for questions. Anyone would like to start off? Yeah?
Oh, thank you so much. This was a really great presentation. I love the energy. I was curious, with the number of trials, do you think participants experience fatigue?
What we tried to, because that was a big concern at the beginning, so what I did instead was the actual platform where they were performing the tasks, we angled it in a way that their arms aren't lifting all the way up and they get fatigued. Thankfully, no participants actually reported that they felt tired or anything. And additionally, I am in game development, and I know like gamifying an experience really pushes that aside for them. So with a leaderboard and a scoreboard, they didn't even think about it. So thankfully, like from what we've seen and what we from our results and from participants, it didn't seem like a big factor in it.
Thank you.
No worries, thank you.
Anybody else?
In the population of the participants, is there expectation that they have certain knowledge of how to use the controllers versus not everybody is comfortable with controllers, right? So how
That
do you
is true.
take that into consideration?
Yeah, we did get a demographic study through most of it, being able to see who has experience with certain things, and there definitely was a higher take on people not knowing how to use hand tracking. For controllers, people felt more comfortable with it because in their head, they're like, I'm kind of pressing buttons. I'm mapping it, I can get the gist. But hand tracking actually faced more on the never seen this before. So that was something that we noticed behind it, but we didn't want it to stop because we want to test all different users to see how they experience first time. Because a lot of people still don't know hand tracking. Some of them do know controllers, some of them don't. So we want to see overall, but we didn't see much of a difference between those users that did have experience or didn't. But if we see it with our future work, with more factors involved, it might take a bigger play on it, which we definitely want to look into. Thank you.
You can still do one more question. Anybody else? Okay. Well, I have one. I'm interested in your current work, the glove. If you can go back a little bit, just to show. So is it a hybrid where you provide some haptic feedback?
Oh, my haptic, this one?
Yeah. Can you talk a little bit more about that?
Oh my gosh, yes. Oh, I was waiting for someone to ask me about future work. I was itching. Okay, thank you. So basically what we're trying to do is we want to add haptics because we thought about what difference would it feel for users if they felt a response with a mismatched avatar? Would it still make them feel like, oh, this isn't very realistic behind it? Or would it actually enhance it? Would that break the bond, like that difference between misalignment and alignment behind it? So we're actually having controllers and hand tracking with haptics like as a main independent variable. So each one, they'll be able to sense it. We're aiming to do impulse, vibration, and no haptics at all to be able to see whether that makes a difference, how it plays within their actions, their performance, or experience. But yeah, it was difficult to get it to work with the hand tracking. I underestimated it a lot, but we managed to get somewhere, which is great. So yeah, we're basically taking the exact study I explained and just adding more to it to see what changes within the experience and performance we saw.
Thank you so much.
Thank
Another round
you.
of applause, please.
Thank you so much.
Hello. Good afternoon, everyone. I'm Matthew Castellana from the Center for Visual Computing at Stony Brook University, and today I'll be presenting Oxyscope, a handheld augmented reality tablet that serves as an auxiliary display for large-scale display systems. This work addresses a fundamental challenge in collaborative visualization: how to enable multiple users to explore personalized views on large wall displays without interfering with each other. So large wall displays are an extremely useful way to visualize and interact with complex data in a collaborative setting. Thanks to their scale and display area, these displays let multiple users simultaneously work on expansive, high-resolution data. They enable collaboration through natural interactions. People can walk around, people can talk, point at things, etc. And as everyone is working together on the same display, it can improve discussion and collaborative sense-making. However, this same shared nature that makes them powerful for collaboration also creates significant challenges when users need different views of the same data. Let me illustrate with an example. Imagine two analysts examining urban data on a large wall display, which is currently showing a side view of some skyscrapers. One is interested in visualizing an overlay of infrastructure risk per building, and the other is interested in visualizing population density per building. Now, these two views cannot coexist simultaneously in the same space on the same large wall display. Sure, you can place them side by side. It is a large wall display after all, but if the spatial context of the placement matters for the visualization, as it does in this case, that's not feasible. So what can we do? Well, one solution is provide each user with their own personalized view. The great thing about this is that depending on the implementation, it can maintain the shared underlying context. For example, here users can see the original view as well as their personalized view. Now this solution has been explored in various ways among various works. I'll present a few examples here just for illustration. For example, through handheld magic lens systems, which create localized view transformations. This example shows Paper Lens, which uses tracked paper sheets above tabletop displays to reveal different data representations. Other versions use tablets, which provide additional functionality, for example, touchscreen interfaces. Another type of approach uses AR headsets for per-user view personalization, which can be effective, although headsets can be expensive and, depending on use case and the type of headset, can impede user interaction to some person-to-person interaction to some extent. Shown here is work by Reipschlager et al., which augments a large wall display with various graphs and functionality. Now, we reviewed approaches like these for our own large wall display, and for applications we were collaborating on with domain experts. We saw works where displays were augmented with 2D graphics. We saw works where displays were augmented with 3D graphics. We even saw works where 3D graphics were extruded from the 2D display. But what we were not able to find, and this is something that we wanted to do, was something that augments a large wall display's virtual content directly. That is, something that provides a perspective correct augmentation that looks as if it's part of the original rendering of the display. And this is what motivated us to create Oxyscope. So you can see here that the large wall display is showing a 3D city with a satellite image as the terrain texture. However, each user has their own view of the display based on what they would normally see through the tablet's camera, but with their own relevant augmentation for the terrain texture. And that augmentation is not including content in the scene that it shouldn't be, such as the 3D buildings. In effect, it's as if we applied the augmentation to the virtual ground itself directly. Now, this approach has the advantage of minimizing disruption when transitioning between tablet and large wall display. The tablet is essentially serving as a magic lens for the wall itself. In the process of developing this Oxyscope paradigm, we also developed a time warp technique to facilitate this approach on a distributed tile display. And we also conducted a user study to try and gauge whether this provided a benefit. So first, let me take you through the pipeline. How do we accomplish this? Here's a look at the pipeline overall, and I'll take you through it step by step. We start with a one-time initialization where users scan an image marker on the display, like a QR code. And this establishes the coordinate transformation between the tablet's AR system and the wall display's virtual space based on a pre-provided layout of the large wall display. Once initialized, the tablet continuously tracks its position and orientation, aka pose, and streams this to the master node. When a user points at or selects something on the display, the master forwards this information along with the pose to the appropriate client nodes in our cluster. Instead of changing what's on the large wall display, each client renders the personalized visualization in the background. And the rendering process for this on the client node works something like this. So first, content is rendered for the large wall display. It's still displaying after all. And then for each user, each display's camera enables that user's augmentation in the scene temporarily and renders an additional intermediary texture with the same resolution, height, width, pose, etc. And that texture is displayed in scene and captured by another virtual camera at the tablet's position. So the resulting frame then streams back through the master to the tablet for display. Now, you'll notice that there's a lot of data transmission steps in this process, from tablet to master to clients, then back to master, and then to the tablet again. So even though everything is on the same network in our large wall display facility, latency still plays a role. By the time the tablet has receives the rendered image for one pose, the user may have moved to another, and that can cause misalignment. So what do we do to address this? Our solution is a two-stage time warp mechanism, showed here in a simplified scenario to better express it. The tablet starts by generating an ID for the pose that will be used to render the AR frame, and then stores the pose using that frame ID. It then sends the ID, pose, and touch info to the master node, which stores the pose for that ID as well. Meanwhile, previous stages of the pipeline continue to operate. The aux continues to generate new frame data and sends them to the master, and the master sends the information it has to the clients. The clients use the provided pose to render a personalized frame, as I described before. This render depends on the tablet's pose and whether or not the display is in the tablet's camera view. In this particular example, one has half of their display in the view and the other has their other half of the display in the view. These rendered frames are sent back to the master along with their IDs as new information continues to course through the pipeline. Now on the master, we know the pose of each display at frame 2 and for frame 0 thanks to this stored pose dictionary. So we can reproject or time warp the frame and then composite them together into a merged frame, which we give the most recent ID found on the master. The merged frame is then sent to the tablet as the previous pipeline stages continue. And once there, we do another time warp and then send the frame to be overlaid on the tablet display. So let's take a look at some example use cases. Our first one is collaborative medical visualization. The video shows how the tablet can be used as a cutting plane for the volume. On the top right, you can see a bit of how you can use the cutting plane from different angles, but it's still looking as if it's being displayed by the large wall display. And on the bottom right, you can see the same functionality with 2 users and 2 different transfer functions. Our second use case is urban flood simulation visualization. We collaborated with Stony Brook's School of Atmospheric and Marine Sciences and developed an application that simulated flooding on a satellite map on the large wall display, where community stakeholders could explore how flooding affects their communities by getting information about various demographics, landmarks of interest, evacuation routes, and more using the tablet. The application was generally well received, with participants mentioning how easy it was to maintain context while pulling up various sub-visualizations. Now, to validate whether our approach was beneficial, we conducted a controlled study with 24 participants working in pairs, and the task was city data exploration. For each trial, we displayed 1 to 4 cities on a display, each of which has a default view seen here, and several alternative views that show some simple data about population or industry within the city. Each pair of users worked on their own separate tasks, interacting using a 3D spherical cursor and answering questions directly on their tablet. Our primary interest was comparing the unique functionality of Oxyscope with the personal display capacity against a baseline where the tablet simply served as a method of interaction and controlling the shared display. So here you can see the baseline. The tablet simply serves as video pass-through, where you can do selection and input. And in this scenario, only one person could control the view of a city at a time. And here you can see the Oxyscope's personal display functionality, where each user was able to see their own relevant data regardless of the other user's actions. Participants completed multiple trials where we systematically varied several parameters, numbers of cities, the number of data views the users needed to accomplish their task, and whether they had any shared views, that is, like whether they could piggyback off of another user's view to answer their question. We hypothesized that Oxyscope would have advantages in completion time and accuracy when users were competing for the same information, same area on the large wall display. And the results confirm our hypothesis partially. You can see in the figure regarding completion time, there's consistent improvements with Oxyscope. Overall, we found that task completion was about 2 seconds faster per task. It may sound modest, but it adds up over extended analysis sessions, and it's statistically significant. We saw some slight signs that accuracy improved a little bit, but that was non-statistically significant. We'd like to do additional testing and trials with that. And we also collected quantitative feedback, both in this user study and from the previous applications. Overall, users described the interaction as intuitive. They liked the personalized display aspect, and they also felt that using it caused less disruption to the shared reference display, as well as to their fellow participants. So thank you all for listening. I'm happy to answer any questions now or anytime during the conference.
Enough time for one question, if anyone has any.
Hello, Maria Gorlatova from Duke University. Thank you so much for this exciting presentation. It's really cool, like the magic lens concept for large wall displays. Really awesome. I had a question. Why? So it seems like the time warping that you would need here is fairly standard. Why did you need a new approach? Why were standard time warping approaches not sufficient for you?
So let me repeat the question just to make sure I unheard it. Why do we need a new approach as opposed to existing approaches?
Yeah. So and what's the key novelty, and why was that needed?
So going back to the flood simulation visualization. So this is an initial version of an application that we're still developing with the School of Marine and Atmospheric Sciences. And again, like I said earlier, let me skip back. So one thing that we wanted specifically for this application was the ability to overlay augmentations that look like they're augmented reality, like augmentations on the virtual scene itself that can go essentially behind objects in the scene. So you see here with the heat map, it's clipping around the building, so it's a lot easier to overlay and work with, and we weren't able to find things that did quite that, and so we're hoping to incorporate that into future versions of this flood simulation application.
Thank you. So that's it for today's session. Please give another round of applause for all the presenters and all authors of all papers. I believe it's another break, until we resume at 5:30. So thank you for joining this session.